In this lecture, we shall consider the formal theory of quantum mechanics, and this is known as wave mechanics. Let us first discuss about the short history of emergence of quantum mechanics. During the 19th century, many of the great advances in physics of the 18th century were consolidated and extended. In addition, the theory of electromagnetism was completed by Maxwell. Except for a few unexplained effects or anomalies, there seemed little more in terms of fundamental physics to be done by the beginning of the 20th century. Yet, it is precisely in the year 1900 that quantum theory starts with Planck's formula for black body radiation. Soon there were a host of experimental results, both new ones and earlier ones, that again attracted attention. All of these pointed to flaws in the physics of the 19th century. In almost all cases, these anomalies resulted when Newtonian mechanics and electromagnetism were simultaneously involved. In trying to elucidate these various experimental facts, a new theory of physics, quantum theory, was born. German physicist Max Planck publishes his groundbreaking study of the effect of radiation on a black body substance, and the quantum theory of modern physics is born. Though physical experiments, Planck demonstrated that energy in certain situations can exhibit characteristics of physical matter. According to theories of classical physics, energy is solely a continuous wave-like phenomenon, independent of the characteristics of physical matter. Planck's theory held that radiant energy is made up of particle-like components known as quanta. The theory helped to resolve previously unexplained natural phenomena such as the behavior of heat in solids and the nature of light absorption on an atomic level. In 1918, Planck was rewarded the Nobel Prize in Physics for his work on black body radiation. Other scientists such as Albert Einstein, Niels Bohr, Louis de Broglie, Erwin Schrödinger, Paul Dirac, and Heisenberg advanced Planck's theory and made possible the development of quantum mechanics, a mathematical application of the quantum theory that maintains that energy is both matter and a wave, depending on certain variables. Quantum mechanics thus takes a probabilistic view of nature, sharply contrasting with classical mechanics, in which all precise properties of objects are in principle calculable. Today, the combination of quantum mechanics with Einstein's theory of relativity is the basis of modern physics. Now we discuss about the postulates of quantum mechanics. Quantum theory can be formulated according to a few postulates, theoretical principles based on experimental observations. The goal of this section is to introduce such principles together with some mathematical concepts that are necessary for that purpose. To keep the notation as simple as possible, very often expressions are written for a one-dimensional system. The generalization to many dimensions is usually straightforward. Usually there are 5 postulates of quantum theory. These postulates are stated and explained in this section. So we shall now study postulate 1 first. Any state of a quantum mechanical system can be described by a mathematical function as a function of position and time, where x is position vector or displacement vector and t is time. Any state of a quantum mechanical system can be described by a wave function, this psi, where x is the position, as I said, and t is time. This function psi is usually a complex function. Known as wave function or state function of this system. Usually a complex function. That means it has real real part and imaginary part. Usually a complex function, and it has no direct meaning. But modulus square of it gives the probability density of finding the system at position x and at time t. So if we take the modulus square, we shall not take the square because psi is complex. So if we take psi square, it will be a complex quantity and it will have no meaning. So if we take complex modulus square, it will be a real quantity and it will have meaning. And the meaning is modulus of psi square is the probability density of finding the system in the state psi at position x and at time t. The state function psi must be continuous, actually psi and its first derivative with respect to position continuous must be single valued and psi must be, and the is square integrable. Okay, so these are the these properties of the state function. So these are the properties of the state function psi. This is A, this is B, this is C, this is D, this is E. This one is figure 2.1. What we see in this figure, say let us suppose that we have, this is for simplicity, this is X and this is psi. And you see this curve A is continuous and its first derivative will also be continuous, but you see curve B, it is continuous, but the first derivative of B will not be continuous. And curve C, this is of course discontinuous, and curve D, it approaches towards infinity. So the square integrable, it does not satisfy this condition. Psi must be square integrable, because if you take, this is psi, so if you take modulus square of psi, it will go to infinity when we increase position. And here you see this is not single valued. E is not single valued. For a particular position X, okay, there will be more than one values of the function. So only curve A satisfies the above conditions. So this curve A only can be considered as a state function or wave function, whereas curve B, C, D, and E, they do not represent state function or wave function. Now we said that the modulus of psi square gives probability density. Let us suppose rho is the probability density. That means probability per unit volume. So the total probability will be obtained from this. If you consider dV is a small volume element, then this is modulus of psi square dV. Okay, so this is total probability. And if psi is normalized, we shall discuss about normalization of state function or wave function later on. If psi is normalized, then this total probability must be equal to 1. This condition, sometimes we call it normalization condition. Okay, if a wave function or state function is not normalized, then we can make it normalized by multiplying the state function by a constant. and then we apply that normalization condition, and we can find the constant, and then you multiply the given wave function by that constant, then the new function will be the normalized wave function. I will show this to you just a moment. If psi is not normalized, then say C psi is normalized. Therefore, modulus of C psi square dV equal to 1. This is the normalization constant. And we bring this modulus of C square outside the integral sign, so we'll have this. So from this we can find the constant. Constant C we can find out from this. We can find from this C. Now I should mention here that this integral, if system is in 1D, one dimension, then we will have this will be minus infinity to plus infinity, and this is dx. If this system is two dimension 2D, then this one will be replaced by two integrals. One is over x, the other is over y. Similarly, if the system is in 3D, then this will be replaced by three integrals, and the limits will be minus infinity to plus infinity. That means you'll have to integrate over the whole space, and dv will be dx into dy into dz. Okay, these things will be clear to you gradually as we proceed. Any wave function psi which has unit norm, which has the property just we have described the normalization condition. Normalizable wave functions are those with finite norm. That means if the wave function is not normalized, then this will be a finite number, a finite value. Okay, that means it should be less than infinity. This is square integrable. This means square integrable. Square integrable. Okay, let us consider superposition or principle of superposition. principle of superposition. If we have two state functions, psi1 and psi2, then their linear combination will be a new state of the system. That means new state psi will be written as this, where C1 and C2 are complex constants. Okay, this is all for postulate 1. Now we discuss postulate 2. Any physical observables can be represented by a linear Hermitian operator. Now we must understand what is physical observable. Physical observable are position or displacement, linear momentum, angular momentum, kinetic energy, potential energy, and finally total energy, total mechanical energy. Okay, these are known as physical observables. Physical observables means they can be measured, measurable property of the system. Okay, then we need to know, now we understand what is physical observables. These are the physical observables. We now need to know the linearity of operator, linear. So with these words, and Hermitian and operator. Some of you may already know what is an operator. For example, we have differential operator, d by dx, differential operator. Okay. Similarly, you can have cosine, cos, logarithm. These are operators. Unless you put there is something in the argument, there will be no meaning of cos, sine, logarithm, etc. So these can be considered as operators. Okay, and if an operator acts on a function, gives a new function, we must know about this quantities operator. say A is an operator. When acts on a function, it gives you another function. Then we call this operator. An operator. Operator is usually denoted by putting a hat or cap over the physical observable. This A operator corresponds to the physical observable A. Okay, now linearity. Linear operator. If for an operator A where C1 and C2 are complex constants, and if this equal to C1 A operator psi 1 plus C2 A operator psi 2, then A is a linear operator where C1 and C2 are complex constant. Okay, third we have Hermitian operator. To define Hermitian operator, we must define inner product of two state functions. To define Hermitian operator, we need to define inner product of two state functions. Okay, then let us define inner product. If we have the inner state functions are psi and phi, then inner product of psi and phi is denoted by this, and you have to integrate and take the first one's complex conjugate, and then the second one, and this is volume element. If it is three-dimensional, then we'll have to take three integral signs. If it is two-dimensional, then we'll have two integration signs, as I discussed this before. Okay, so this is the inner product. Now we are ready to define Hermitian operator. If the operator A satisfies the following, that if you take inner product of this A psi and phi, and if you get this, then we say that A is Hermitian. That means if you have A operator with psi left state function, and which is equivalent to the the operator with state function phi, then we say that the operator A is Hermitian. This is the end of this lecture. In the next lecture, we shall elaborate on the physical observables and their corresponding linear Hermitian operators. We shall also study the other postulates of quantum theory.